Bismillahirrahmanirrahim. So we have started the basic filter design in the last class. So we have talked about in detail based on M-point moving average system, you can say about the filter. And at the end of that session, we have found that it actually works like a low-pass filter, and we have also draw the phase representation for 5-point moving average filter, as you can see here. Today we'll start with some basic of the filter design, practical filter design with the Z transform representation with the help of that, the transformation. That will definitely help us to understand the filter. Okay, so this is a fundamental architecture of a filter. We know that the filter have different region named as pass band. We have the transition band. We have the stop band. So they have their own characteristics, and we are putting the we are mentioning the pass band from here. This is of course a low pass filter. So the pass band, the definition of the pass band, we are putting a cutoff frequency here. We need to define the cutoff frequency, where this is the 3 dB point. It can be mentioned as a minus 3 dB, as well as this is from the gain point of view, that can be written as 1 divided by √2 or 0.707. Okay, in different manner we can. So in the dB scale, that is minus 3 dB. In the gain scale, that is 0.707. Okay, we have the stop band, and the stop band gain also need to be represented with a value, whether it is in dB or in the amplitude. And of course, in conventional way, we are in conventional pattern, we are representing the band of the frequency, band of the filter from 0 to pi. Of course, you know that the pi 0 to pi actually contains all the frequency component, because that is a relative frequency. This omega represent the ratio between the actual frequency and the sampling frequency, because omega is equals to twice pi small f, and twice pi small f is equals to f divided by fs. So you can increase the value of the fs, and you can determine what would be the value of the pi for a particular case. So we have learned those things in our previous sections. Okay, so this is an example. For voice processing, we may choose, this is from the practical data, the cutoff frequency could be 3.3 kilohertz, and the stop band frequency could be 4 kilohertz. So this can be 3.3 kilohertz, and this could be 4 kilohertz. The pi represent the 20 kilohertz. The maximum frequency we can consider, that is 20 kilohertz. What does it mean here? I would like to represent this pi. Of course, this is omega. It's represent twice pi f divided by fs, where this f can be represented as 20 kilohertz. That what does it mean by this statement? The pi can be represented at the 20 kilohertz point. And again, for, as I have already mentioned, from 0 to, there is a mistake, 0 to omega c, the frequency band, 0 to omega c. What would be the amplitude? The amplitude would be in between 1 to pi. Now 1 to alpha, where alpha is 1 divided by √2. That means the cutoff frequency, the 3 dB point. So in between this, the amplitude, it can be very flat, like 1. So for the ideal case, but for the practical case, it might definitely, it will be decayed, and in other cases it might changes like this. It can have like this. So we'll discuss about different type of filter in the upcoming semester, so where we will learn about more detail about those characteristics. However, in general, this is the tolerance in the passband. The amplitude can be fluctuated between 1 to alpha, where alpha is the minus 3 dB point, 3 dB gain. So, and these are the practical values for the voice processing. The beta can be given as 0.001 or minus 60. This is 60, minus 60 dB point. Okay, you need to define it for designing your filter. Now with a practical example, we can start. Let's say the xn is given like this. This is in general. In general, it can be written as, let me amplify a little bit. Yeah, this could be fine. So xn is equals to a cos omega 1 n plus b cos omega 2 n. From the notation, you can find that we have two frequency component here. One is omega 1 and one is omega 2, and they are purely sinusoidal signal, and they have an infinite range of the value. Okay, so in the frequency domain, you can, if I convert this time domain sequence to the frequency domain, so we'll get to a stem. Now, what is our task? Our task, we want to pass omega 1 and reject omega 2, where omega 2 is higher than omega 2. So if I draw it in the frequency domain, in the omega scale, let's say this is omega 1 and this is omega 2. We have two values are there, and omega 2 is higher than omega 2. So we need to pass omega 1 and reject omega 2. So we need to build a definitely a low pass filter, but that is not the only way to get omega 1. It can be like this, or it can be a band pass filter as well, isn't it? So if we design a band pass filter as well, we can take it. So this is the concept what we need to do. In other case, if we can design, or we can take a impulse response, we can collect the impulse response in such a way that it only give you one output at the location of y1 and give 0 at the location of y2. That is also enough to design a filter. Basically, we are talking about the output. Whenever we are talking about the output, this output is a combination of your input, which is an arbitrary value, and you have the impulse response. You know that the convolution sum between input and impulse response give you the output. Now you know about your input already. You need to analyze your input, and after analyzing your input, you can understand which kind of impulse response you need to restrict or to collect this part and to block this part. That is our fundamental target. Okay. So before going to this example, let me give you one idea for LTI system, which will help us to design the filter in the time domain, from the time domain perspective. Okay, starting from the concept of the convolution sum. Of course, this is the equation for the convolution sum. This is the output, where this is the input and this is the impulse response. If we take the input as xn is equals to e to the power j omega n, we just take it as an example. And this is very logical to take this kind of example, because in this example you have the in xn you have the cosine signal, that means a sinusoidal signal with a particular frequency. The frequency is omega, as we can write it like here. This is cos omega n plus j sine omega n. So I have probably you can draw this e to the power j omega n, and you will find the output. Whatever the case, we are taking a input which is a unit of a particular signal. What I have meant, if you have some signal like this, okay, purely sinusoidal, you can represent it by this. In another way, if you have any other kind of signal which is a combination of different sinusoidal signal, in that case you can take, this is x1, you can take another signal x2 with another frequency. So this is the unit of a particular signal. You can make a combination of x1n plus x2n and so on if you need for a particular signal construction, because as we already know that for this kind of signal, where this is not a purely sinusoidal signal, you need a number of signals with coefficient. Of course, you need a1, a2, and other coefficients. Since this is a LTI system, I'm talking about this LTI system, if you have a number of x1, x2, x3, you can straightforward go for the linear combination of that and to get the output. That is why this is logical that we start with a sinusoidal signal. If it is true for the sinusoidal signal, it is also true for any other signal. Let me proceed. So in this equation, let me give the equation number 1. In the equation number 1, if we put this x value, then what we can get? We get this e to the power j omega n into e to the power minus j omega k, because we have n minus k. So if you put n replaced by n minus k, then of course you find this term, and then hk is there. Just proceeding a little bit more, as you can understand, these two terms. In these two terms, this is independent to the value of k. That's why we can take out of the summation, and we can write it like this. If you concentrate on this term, this is nothing but the Fourier transform h omega, Fourier transform of hn, because it is multiplied with e to the power minus j omega k. So this k can be replaced. So if you have the doubt, you can put it like n, n, and n. So now you can find that this is exactly the Fourier transform of hn. So now this can be, so I have written it here as well. And now this output can be written as this. What is this? This is your input, and input multiplied by the impulse response, the frequency, the Fourier transform value of the impulse response, and that is the output. So we got this output. Okay, it is explained here why we have write it like this. So from this concept, mentioning this concept, if the input is like this, the output should be like this. Now, if we talk about only the real part, then of course we have the output like this, where the real part is we have the magnitude, and we have from this we have the magnitude, and the cause we have omega, the phase part is there. So if you can consider what is the amplitude what is the amplitude of this signal? The amplitude of the signal is 1. And what is the output? The output should be h omega, the amplitude, and then the amplitude from the cos omega, and that is 1. That's why we are not mentioning anything. And then the input signal cos, of course, the phase will be shifted according to the phase of your impulse response. That's why the phase omega n, it was previously been there, plus the phase of the h omega for a particular case. Okay, so we have how the phase will be shifted. We have cos, previously we have h omega, and now h omega will be added together. So this is the phase components are reflecting here. What is the magnitude component? As we have found that the magnitude is 1 here, and the magnitude, we got the magnitude from there. So h omega, the magnitude over there. Similarly, in the imaginary part, if we consider the imaginary part, we have the phase components are reflected here, and this is the magnitude component. In this way, any inputs can be represented like this. If you have in the time domain, if you have any input value, you can represent it like this. Okay. In practice, try to understand here very clearly. In practice, whenever we are talking about any signal which is not a pure sinusoidal signal, it is a combination of a number of sequence, number of sinusoidal. So it might be a huge number of that. So in that case, we have huge number of this kind of output as well. So practical case is like this. In that case, what we have done practically, we are taking this signal and moving it to the Fourier domain or the frequency domain, all the signals, and the impulse response is also converted to the frequency domain, and then we are analyzing this. For this particular example, means this is a very simple example. It's given like this. We are just considering this as an input and this as an input, and how to take this and how to reject this. We are just showing it just to make the specific idea clear. But in general, whenever we are talking about a practical situation, we have a number of terms are there. That's why the situation will be more complex. However, we start with the simple idea so that we can understand each and every part very clearly. Okay. Okay. Now back to the example. So our example was given like this, and we need to pass omega 1 and we need to reject omega 2, where the CDL of the hierarchy of the frequency is given here, just to understand. Now, according to our last example, what we have discussed so far, we can write in this way. Try to look at this and this output. The output would be like, we have the amplitude. This is the amplitude. Then the amplitude from the impulse response for that particular omega value, because we have the omega 1, then cos, and the phase is omega 1 n plus the phase at that location, h omega 1, plus we have this amplitude b from the input signal and the amplitude from the impulse response for particular omega value, omega 2, then cos the phase of that, omega 2n plus h omega 2, the phase of that. So from this input, considering this input xn and the impulse response hn, any impulse response, we can write this equation yn. And what is the baseline? The baseline is the convolution sum we have shown. So to achieve the objective or the target, of the example, what we need to do, we need to make it 1, h omega 1, the value of that should be 1, and h omega 2, the amplitude, it should be 0. So in practice, it is very close to 1. That's why this is an approximate sign, and this is approximately 0. That is enough. So this term will goes to 0, and this term will make it 1. So that is our target. If we can do so, then this signal will survive and this signal will be rejected. So that is our concept. Of course, that will look like a low pass filter. Okay, that is the concept. Now we are taking a specific example to understand more deeply about the problem, where we are doing just the reverse. Xn is equals to cos 0.1 n plus cos 0.4 n. So from the number, you can find that this is a lower frequency and this is a higher frequency. Now we want to take it and we want to reject this. So which kind of filter we need to design? Definitely we need to design a high pass filter. And for a FIR system, it is mentioned here as an FIR system. Okay, so we know that what we need to do from our previous experience here, it is actually like omega 1 and this is omega 2. So h, you can write it like here, h omega 1. What is that? H 0.1. This is also okay. And sometimes people are writing e to the power j 0.1 n, just to mention that at this frequency, at that frequency, this amplitude, I should write this modulus value. This should be is equals to what? 0. And h e to the power j 0.4 n, that means at omega 2, 0.4 omega, the amplitude should be is equals to very close to 1. That is our target. If we can do so, then we can build the filter. What is the key factor to design the filter? We need to select our Hn, or we need to select our H omega in such a way so that H 0.1 should be is equals to 0 and H 0.4 should be is equals to 1. That is our target. So Hn and H omega, they are the same thing. One is in the time domain and another one in the frequency domain, and that is our target. Now let that this is our Hn. You are just letting that this is our Hn. I can mention you that designing a filter is a trial and error method always. There is no hard and fast rules all the times, and especially for the FIR system. Okay, so that is why it is given here. Example this for a FIR system. In case of IIR system, there are some rules to design the filter. For the FIR system, that is a trial and error method. Just I'm conveying this message, but it will be more clear when we'll particularly design the filter in the next semester. But you can just think of it. In case of FIR filter, we need to just try something and try to check it whether we are at our target or at our goal. If not, then we need to change our strategy. Okay, that is the thing. Okay, so just follow me here. We let that Hn is equals to alpha at n equals to 0, beta at n is equals to 1, and alpha at n is equals to 2. So if we make the sequence here, this is, let's say this is our Hn. At 0 location, what is the value of let's say this is alpha, this is beta, we do not know the value. What is alpha and what is beta? It can be positive or negative. Just let that. This is the value. So in general, I'm taking some value. Now, from there, you can write what is h omega. What is that? It is alpha e to the power minus j omega n. What is n? N is equals to 0 plus beta e to the power minus j omega into 1 plus alpha e to the power minus j omega into 2. Very simple. And that we have wrote here. And this is the output of h omega. Then we can take this part and take alpha common. Okay, so there are some manipulations we have done here, so you can do yourself as well. So let me do it. So from this line, what we can do, we have beta e to the power minus j omega plus, I'm taking common alpha, so 1 plus e to the power minus j twice omega. Let's say this is a fact. So beta e to the power minus j omega plus this alpha, I need to take common e to the power minus j omega. So if I take a common of that, we have e to the power j omega plus e to the power minus j omega. And now you can find that e to the power j omega plus e to the power minus j omega, which is nothing but twice cos omega. So you can replace this part as twice cos omega. And now we can write 2 alpha e to the power minus j omega into cos omega. So I believe you understand in this part, very simple. So we have wrote here, and again, we are taking common of e to the power j omega, and this is the final output for this one. Okay, these manipulations actually help us to understand the whole thing. In this equation, this part is only showing, it is actually dependent on the phase component omega. There is nothing with the amplitude. The amplitude actually depends on this term. So whenever we are talking about h 0.1, magnitude should be 0. This amplitude actually been taken from there because there is no amplitude component built here. We have only the phase component. Similarly, for h 0.4, magnitude should be is equals to 1. That actually came from this part, not from the phase part. So according to that, so as I already mentioned that for omega equals to 0.1, so this would be 0.1. So beta plus twice alpha cos 0.1 should be equals to 0. This is equation number 1. We have one equation. And for the second equation, we put omega equals to 0.4. For that one, we have this equation. And make sure that 0.1 and 0.4, they are in radian, because that is the value of omega. That is the value of omega. Okay. So from these two equations, of course, we have two unknowns, beta and alpha. We can find it. It's very simple. We found that alpha is equals to this and beta equals to this. If it is so, we already let that hn is equals to what? Alpha, beta, alpha, and that was the what? That was the n is equals to 0. So we have got these two values, and we have designed our filter, the first filter. The filter hn, the impulse response, looks like this. This is the alpha, this is beta, and this is the alpha. So that is the impulse response. And of course, we can also write the yn. What is yn? yn is equals to, you have your xn. What was your xn? You know the value of xn, the particular whatever the input, the output is the convolution sum of the impulse response. You can make the convolution sum of the impulse responses as we have done previously. But the main concept is you have designed your filter, and this is whenever we are talking that design a filter, what you need to do, you need to actually find what is the value of Hn. That is the filter design, where there would be some target. In our case, the target was the omega is equals to 0.1 should be cancelled, and omega equals to 0.4 should be taken. That is our target. But whenever we are talking about design a filter, what does it mean? What could be the output of that design process? The output could be, you need to design a particular H omega, and in consequence, you need to show what is the value of Hn. That is the design. So we can congratulate ourselves that we have designed the first filter in the digital domain, and which is a FIR filter. Now from your MATLAB or any other software, if you have this Hn, what you can do, you can find what is H omega, and you can find the frequency domain representation. And if you draw it, you can find that this is of course a high pass filter, where let's say this is a 0.4 and this is a 0.1 in particular value of omega. So that means you can draw the H omega and you can justify yourself. So draw it and justify yourself whether it works properly or not. Since you have this Hn, you can find H omega. How you can find the H omega? The value minus 6.76 e to the power minus j omega n equals to 0 plus 17.45 e to the power minus j omega into 1 plus minus 6.76 e to the power minus j omega into 2. Here this is, of course, this is equals to 1, and we have e to the power, this is e to the power minus j omega, and this is e to the power twice j omega. Whatever the case, now you can draw it in the frequency domain for a particular value, for each and every value of omega, and then you can find that how it looks like in the frequency domain. In that way, you can justify yourself whether you have designed the correct filter or not. Okay, so any confusion up to this with this example? Okay, I believe everything is fine. Okay, so we have designed our first filter with some target with a specific example. Now we start with simple filter design or digital filters, and first we start with the FIR type filter design. What is FIR filter? I have already mentioned that in case of FIR filter, you don't have any pole locations rather than the center. So the pole, all the pole locations, if you have the any pole location, it can be in the infinity. So that means in the scenario, okay, let me show it with the example. Okay, so FIR filter, we'll design FIR filters. Let's start with Hz is equals to 1 plus Hz is equals to 1 plus z to the power minus 1. We know that what is z. From here, we can write 1 plus 1 divided by z So we can write Z1 plus Z, or Z plus 1, whatever the case, Z plus 1. So from this equation, we can find the pole locations and the zero locations. What is the zero location? The zero location is Z is equals to -1. This is the zero locations. And what is the pole location? Z is equals to 0. What I mentioned here, in case of FIR filter, all the poles are in the center. So we have, if we want to draw the pole location, that is in the center. What about the zero location? On the unit circle, if I draw the unit circle, the pole, the zero location at -1, at Z is equals to -1, because Z equals to +1 is this point and Z equals to -1 is this point. Z is equals to +J is this point. Okay. Okay. So for understanding what we always do, we are designing our filter from the Z plane representation, where we always take into account that all the poles and the zeros are inside the circle. Basically, all the poles of course should be inside the circle for the causal system. Otherwise, it will be unstable. And what about the zeros? Yes, zeros can be outside the unit circle as well, but for this case, we are putting on the unit circle. Okay, so that is our first filter, the system. First of all, the system, and by writing the system, we can also write the poles and the zero locations, as I already mentioned here. So how we can draw the poles and the zero location. Whenever you have drawn it, the next step, what we can do, from Z domain, we can go to the Fourier domain, and we can write 1 plus e to the power. What is Z? Z is equals to R into e to the power minus j omega. It should be plus e to the power j omega. So here R is equals to 1, so that the Z domain and the Fourier domain exactly representing the same thing. As we have already know that when the R is equals to 1, then the Z transform and the Fourier transform are the same. So here the magnitude is 1, so we are targeting the unit circle. If we do the calculations, we can find that at omega equals to 0, this represent what? At omega equals to 0, this represent 1 plus this is again 1 at omega equals to 0. So it gives 2. So since it is a 2, it shows the maximum value here. Okay, we'll talk about the maximum or minimum. Since this is 2, that's why we are multiplying with half before that. And that is why we are putting a half there. So that half into 2, that will give you 1. So whenever we are talking about the filter, try to understand that filter will not work as an amplifier. So in the frequency domain, whenever we are drawing the magnitude response of a filter, what could be the highest magnitude? The highest magnitude is always 1, not like 2. So in the given example, if we are not putting this half there, at omega equals to 0, which location in the pole 0 plane or Z plane, this is the pole location, and this is the 0 location, and this is the pole location. At omega equals to 0, that means at this point in the frequency domain representation, at omega equals to 0, what is the amplitude? The amplitude is equals to 2, which is unacceptable. And this is the maximum value for this filter. So to normalize this, what we need to do, we need to multiply it with half, and that's why this half is introduced here. For omega is equals to pi, try to understand, at omega equals to pi, that means at this point, what happened? Omega equals to pi. So elaborate this term in cos and sine. So cos pi, what is the value of cos pi? That is -1. And so -1 and +1, it actually gives 0. So that's why we got 0 at omega equals to pi. So if we consider here at omega equals to pi, the amplitude is equals to 0. So that's why if you calculate it from 0 to pi, what we can find, this equation, you can put the different value of omega, you can find that the output looks like this. And that actually been shown here. In this amplitude response. So from this equation, you can write this equation very easily with the help of Euler's formula. So take the common of e to the power j omega by 2 in this equation. So it will give, let's say, half e to the power minus j omega divided by 2. Then we have e to the power j omega divided by 2 plus e to the power minus j omega divided by 2. So from there we can find half e to the power minus j omega divided by 2 into twice cos omega divided by 2, and these 2 will cancel, and eventually you'll find this equation. Okay, so we have this equation, and now you need to plot it. You do not have any amplitude quantity there. So to plot the magnitude response, definitely you need to consider this. So as you can find that it is exactly the cos signal. So plot it for omega equals to 0. What would be the value for omega equals to 0? Cos 0 is equals to 1. For omega is equals to pi by 2, put pi by 2. It gives 1 divided by, so pi by 2, pi by 4, that means it gives what is 45 degree probably. So whatever the value, you'll find the amplitude is equals to 1 divided by √2. At omega equals to pi, that is pi by 2 is 90, that is equals to 0. So this is how you can plot the magnitude response. Do we need to proceed more? The answer is no, because we have already reached up to the pi, because pi is our range of view. That is the magnitude response. From this equation, the phase response, which part actually gives the phase? So if I write in this way, this equation, this is h omega magnitude, it belongs to cos omega divided by 2. The phase, the second part, the phase of h omega, it belongs to e to the power minus j omega by 2. So this is minus omega divided by 2. That is the phase. So at omega equals to 0, of course, it will be 0. At omega is equals to, let's say at omega is equals to pi, what will be the value? Minus a pi divided by 2. So at omega is equals to pi, the value would be what? Minus pi by 2. And since this is a linear function, you can write a linear straight line like this. So that is the phase response of this kind of filter. What kind of filter is that? Try to understand the pole and zero location. This is very important now. Now this is very important. Where is the 0? This is the 0 and this is the pole. You have already learned that from the pole and zero location, how could you draw the magnitude response? isn't it? You know that how to draw the magnitude response. In that case, the distance of the 0 divided by distance of the pole to a particular location. So let's start with this location. You are at there, so that means omega equals to 0. What is the distance? Definitely the distance from the 0 is very high. And what is the value? What is the value? Any of you? What is the distance from the 0? 76.
1.
Is that 1 or 2?
Come 2.
That is 2. So 2, because this is 1 and this is 1. That's why this is 2. 2 divided by what is the distance from the pole? Distance from the pole?
1.
1. So it is equals to 2. And then it actually multiplied, and that's why the whole system, this is for 1 plus z to the power minus 1. That's why we are multiplying a half with that, so that it becomes 1. Okay, and that's why we start with 1 here. It has already been multiplied. This half is already been there, so that's why it is 1. Whenever it moves to this point, which part will decrease? The distance from the 0 will decrease. They will decrease. Try to understand. But the distance from the pole, that will remain constant. So since the numerators will decrease, the whole value will decrease. And that's why it is decreasing. It is decreasing, decreasing, and decreasing more. Whenever this point is superimposed on the 0 point. So let me choose another color like this. When it is superimposed on the 0 location, what is the distance of the 0 on that point? Of course, 0. That is 0 divided by 1, and that gives you the 0 value. And that's why at the location of pi, omega equals to pi, it will be 0. Very simple. Okay, so that will be 0 in that way. So you can understand the process, and from there you can build the concept that whenever we have the pole here, 0 there, 0 means at that location 0, at that location the frequency will be blocked. The 0 represent this. At which frequency? At omega equals to pi, that will be blocked. So of course that will be blocked there. And since there is no 0 here, that will be pass. So from this pole zero combination, I can say easily that this is of course a low pass filter. This is of course a low pass filter. Just to make the idea more clear, if I give this kind of thing, this is the 0 location and this is the pole location. What kind of filter is this? What kind of filter is this?
High pass.
Of course, high pass. Yes, very good. Because at omega equals to 0, it will be blocked because 0 is there. And omega is equals to pi, it will be passed because there is no 0. That's why we can assume that, of course, this is a high pass filter. We'll talk about this in the subsequent section. So this is very interesting. So from the Z plane representation, you can understand it very quickly. You need to be very confident on this process, what we have done, why we have done, why we are putting hub there. So everything should be understood. If you understood each and every part, your life will be very easy. So things are very simple. No doubt about this. Okay, now few things more. If we want to find the cutoff frequency, this is very important. Where is the cutoff frequency? According to the literature, the definition of the cutoff frequency, the amplitude at that moment should be 1 divided by √2. So that is in general. So what is the amplitude? The amplitude is cos omega by 2. So from the equation, we have already established that the amplitude depends on this. So this amplitude, so cos omega divided by 2 should be 1 by √2 at the location of omega c. At the location of omega c. That's why we can write it like this, and from there we can find the cutoff frequency is at pi by 2, and you can draw it here. This is your cutoff frequency, pi by 2. So at the half mark of your whole spectrum, and the amplitude is 1 divided by √2. And the second thing, I always mention that you need to find the HN, that is your filter. So how could you find the value of HN? How could you find that? You have already this, if you can recall, you have this term, or you have this term. So from there, what we can write, this is half plus half z to the power minus 1. This is your hz. So of course, from this notation, we can find that this is at 0 location. So we can write our hn is nothing but half, and this is at the location of -1, z to the power -1, at the location of +1. So at the location of +1, what is the amplitude? Amplitude is again half. So we can write it straightforward from the z domain representation. Similarly to frequency domain representation, h omega is equals to what? Half plus half e to the power minus j omega. What is the value of n? N is 1. So from there, you can also write that, okay, this is at the location of 0, half, and at the location of 1. So you need to write it like this. So this equation and this equation both are equally helpful to find the value of hn, and you can draw it. So if you have your hn looks like this, what kind of filter is this? What kind of filter? We have already established that this is a low pass filter. So you can design a low pass filter like this. So you have half in the location of n equals to 0 and n equals to 1, and that's it. That is a very basic low pass filter. Of course, this is not a very good quality low pass filter, but you have designed that. Okay, the statement is given here. So how to improve the quality of the filter? So you have a low pass filter. This is low pass filter. We have just designed it, where the cutoff frequency omega c is equals to pi by 2. That's why this is a very poor quality filter. How to improve the quality of the filter? So if you concentrate on this figure, you'll find that, okay, this is our design filter, where this is our cutoff frequency. This is our cutoff frequency. Now, if you want to improve the quality of the filter, that might be like this. So this could be the improved version. Okay, let me choose the color like this. So this is the improved version. Why that is improved? Because as you can understand that in that case, the cutoff is the cutoff frequency, the band of the cutoff frequency, the band of the pass band, the pass band is reduced now. You can improve more. You can improve more like this. So it is a more improved or good quality filter, because in that case, the pass band is reduced more. So how could you do that? The one process for the FIR filter, one process is called cascading. For FIR filter, we can cascade. So this is a low pass filter. What is the order of the filter? The first order. And this is another low pass filter, first order. Then you can cascade those two filters, and that will give you a second order low pass filter, which will improve the quality of the filter. So the equations and the calculations are given here. So if you cascade m number of m, 1, 2, up to m, so 1, 2, up to m number of low pass filter, for each and every filter, of course, the amplitude quantity depends on cos omega by 2 for the cutoff omega c by 2. So you have multiplied those things for m times. So cos omega c by 2 to the power m is equals to, what should be the amplitude of that cutoff? Of course, 1 divided by 2, because it remains constant. From there, just do the calculation. You will find the cutoff frequency is this cutoff frequency now depending on the value of m. That means it depends on the number of filters, how many number of filters you are cascading. For m equals to 2, now the cutoff frequency omega c is equals to 0.2. Previously, it was when there is a single one, the omega c is equals to pi by 2. Pi by 2 means half. 0.2 means 0.2. They are reducing. So now this is 0.2 by cascading 3 of those. So if someone asks you how to improve the quality of the filter, of course you can say, okay, the simple method by cascading the filter. Okay, we can move to the next section as well. Again, if we, in the previous section, the hz was 1 plus z to the power minus 1. Now, if we have 1 minus z to the power minus 1, how it looks like, z to the power minus 1, then 1 minus 1 divided by z. So z minus 1 divided by z. Where is the 0 location? 0 location at 1 plus 1, and the pole location at definitely 0. So if I draw it here, where is the 0 location? At 1, I have shown it, and the pole location at 0. From there, you can understand very quickly that, okay, it is a high pass filter. To normalize the things, again, we need to multiply it with half. Just this half is just to normalize the things, but this is very important. Otherwise, your filter might works like a amplifier as well, and that is very harmful for the signal processing. Your filter maximum gain could be 1, otherwise you are in a trouble. Okay, so if you allow me, I just go a little bit faster for this section. So the same process. Now for omega equals to 0, we got 0, and omega equals to pi, we got 1 from this equation. You can do the calculations, you can find it very simple. And by doing this calculation from using the Euler's formula, we find this kind of equation where, again, you can find where is the amplitude quantity. You can find the amplitude quantity from there. So if I write h omega magnitude, that will be sine omega by 2. It depends on this. If I talk about the phase of h omega, it depends on now two factor. That means we have theta value. That means we have j, as well as we have e to the power minus j omega divided by 2. So this omega divided by 2 is dependent to the value of omega, but we have also j. What is j? In this case, the j represent pi by 2. So if I show you this in this way, for omega equals to 0, we are talking about the phase. The magnitude response, it definitely depends on this. Okay, this is very simple. You can draw it. And of course, this is a part of the sine signal, and you need to extend it up to the pi. Okay, that's it. Whenever we are talking about the phase at omega equals to 0, this is j e to the power minus j0. So we have j, and j is equals to pi by 2. So that is the angle. At omega equals to, so that's why it start with not with 0, that start with the angle pi by 2. Now at omega is equals to pi, this is at omega equals to 0, we have found it. At omega equals to pi, it will be j e to the power minus j pi by 2. Now, how we do the calculation? J is equals to pi by 2, and then multiplications means addition, then we have minus pi by 2. So in all the cases, if we consider it, so it gives 0 degree. So it will give 0 degree. So all the way, what we can do, this j e to the power minus j omega by 2, it actually been represented like this. Pi by 2, j represent pi by 2 plus, in this case, minus omega by 2. That is the phase quantity. So the phase with respect to omega is equals to this. At omega equals to 0, it is equals to pi by 2. At omega is equals to pi by 2, it is equals to 0. We have. So we have a ceiling over j pi by 2 in this case. So be careful for the phase value all the time. And of course, with the similar notion, you can also find the cutoff frequency. What is the cutoff frequency again? Sine omega c divided by 2, it should be 1 divided by root 2. From there, you can find that omega c is equals to pi by 2. Can you tell me what is the value of Hn? Hn should be half and
minus half.
Minus half. Excellent. And that is your filter. You have designed your high pass filter. What kind of filter is this? FIR or IIR? The pole 0 locations I am showing you. This is the 0 location. What kind of filter is this? In case of FIR filter, all the poles are in the center. So of course, this is a FIR filter. We have started with that. So concluding with this remark, that if this is a low pass, then this is a high pass. What is the difference? This is plus and this is a minus. And of course, you can understand from the pole 0 locations, not from the equation, from the pole 0 locations, where is the high pass and where is the low pass. This is of course a high pass or low pass. This one is low pass filter because it will pass the low frequency and block the high frequency, and it will block the low frequency, pass the high frequency. So this is high pass filter. Okay, I believe this is enough for today. Inshallah, we can start from this section in the next class. Thank you for your participation.